Hello, and welcome back to this week's episode of Physical Phenomena Explained, where we'll be discussing one of our favorites, none other than the majestic hydraulic jump. As always, we're your hosts, Hannah and Monica, and without further ado, let's jump into it. In our project on hydraulic jumps, we will be outlining the following topics. What is a hydraulic jump, followed by a video example? How does it work, with visual aids? What influences it? Naturally occurring jumps, and some real-life applications.
Hydraulic jump is a phenomenon in fluids that occurs due to changing flow velocities. A common example in everyday life occurs at the bottom of your sink. Essentially, water from the tap flows down and hits the sink at a high velocity, rapidly spreading out from the point of impact and then slowing down, creating a bump in the ring of water, the hydraulic jump itself. This is a simplified model that is not representative of typical situations, but it is a useful model.
A more accurate demonstration of the phenomenon can be seen in rectangular channels with high-velocity water flowing in them. As the block is added, it disrupts the flow, and we can see the hydraulic jump forming and moving back in the channel, as more of the high-velocity flow meets the slower-flowing water, somewhat like bunching up in a traffic jam.
Researchers Merzen and Chanson formally define it as a rapid and sudden transition from a high-velocity supercritical open channel flow to a subcritical flow. Supercritical and subcritical flow are defined by looking at Froude's number, which is found through the formula F equals V over C, where V is the flow velocity of the water and C is the wave speed of the traveling waves, which is frequency times wavelength. When Froude's number is greater than 1, flow velocity is greater than the wave speed. This is a smooth laminar flow called supercritical, since the water is moving too fast for there to be visible waves or any waves traveling in the opposite direction. When this ratio is less than 1, we're considered to be in subcritical conditions, meaning the wave speed is greater than the flow velocity, and the result is a turbulent flow with visible waves, often the higher section after the jump in diagrams.
The transition from supercritical to subcritical, or laminar to turbulent, is the hydraulic jump itself, and the increase in height that comes with it occurs at the critical point, where Froude's number is equal to 1. With some manipulations of the flow rate formula, Q equals AV, the momentum flux formula, and the ratio of heights before and after, the hydraulic jump can be represented as the formula shown here. This shows that the larger Froude's number is, the larger the height difference between the initial and final height. Researcher W.H. Heger states that creating turbulence results in sound being produced and a loss of energy as a result. Here is a diagram of an experiment similar to the video clip previously shown that highlights the changes in height and velocity.
As previously mentioned, hydraulic jumps occur when Froude's number switches from greater than 1 to less than 1, and this happens when the flow velocity changes, as we are assuming the wave speed of traveling waves is constant. Obstructions, as we saw in the video demonstration, or new friction being introduced at the bottom of the channel can cause the flow to slow down and effectively change Froude's number. In simplified cases of jumps, such as in sinks, it has recently been proven that gravity does not in fact contribute to the hydraulic jumps, despite what was previously thought.
A Cambridge researcher conducted experiments where water was sprayed at flat surfaces in different orientations. He found that the radius of the hydraulic jump did not change significantly with different orientations, demonstrating that gravity was not a factor. Instead, we know that the momentum of the water is counteracted by surface tension and viscous forces.
While we've seen that they can be produced in lab simulations, hydraulic jumps are very common in natural water conditions like rivers as well. Often, rocks in the riverbed can act as obstructions and cause miniature jumps as pictured here. For example, hydraulic jumps were common in the Chiaravagna River basin in Italy, but they often led to harmful flooding of the nearby area. To remedy this, the riverbed was redesigned and a longitudinal dike was created to reduce hydraulic jumps and limit potential flooding.
In other real-life applications of hydraulic jumps, we know that they are great for dissipating energy in man-made water structures, such as at the end of spillways or dissipation basins. As the water slows down, the jump height increases, which is consistent with Bernoulli's principle. Naturally, kinetic energy will therefore decrease while potential increases, as we learned in class. This is excellent for energy control.
Thanks for listening to this week's episode on hydraulic jumps, an intriguing phenomenon that occurs due to a combination of fluid dynamics and traveling waves. Until next week's episode of Physical Phenomena Explained, this is Hannah and Monica signing off.